I'm going to start slowly anyway. Welcome everyone. We are 60 participants connected, so it's time to start. Welcome to this workshop on interpolation and geological modeling methods. I am Simon Lopez from BRGM, which is the French Geological Survey. I am co-organizing this meeting with Nicolas Clausol, which is my colleague at BRGM. And with, you can see him, his activities, camera. This workshop is part of a much larger project, which is called GSEU, and it's a European project. Okay, I'm trying to. Okay, it works. It's called Geological Service for Europe, whose goal is to develop kind of harmonized data and information service between European geological surveys and develop a common European geological knowledge base platform and infrastructure, building on existing facilities that were developed in previous projects such as EGDI, for example. And it's a kind of networking action, basically, with the goal to strengthen the network of national and regional geological survey organizations in various fields and thematics. Between all these fields, there is a work package dedicated to Geological Framework Setup, which deals really with basic geology, trying to have an harmonized vision of geology, geological data, and models all over Europe. And in this work package, there is a task 6.3, which is called Share Methods, Open Tools, Workflows, and Best Practices for 3D Geomodeling and Visualization. And this series of workshops is organized in the framework of this little task. The objectives of the task is to develop and unite the surveys around the 3D geological modeling activities, trying to strengthen a committee which already exists, because there have been already several meetings of the European Geological Modeling Community. So the community both inside and around the surveys. The deliverable of the task is mainly a report, but really what we would like to build is kind of a structured toolbox to perform geological modeling in surveys and tasks around geological modeling. So the report will involve best practices and tutorials on how to change tools and how to use tools in surveys application. So a large part of the task is dedicated to try to evaluate and review the tools that are already available. And this is also one of the main objectives of the workshop that we are organizing. This workshop is the fourth of the kind. The three first ones were between surveys, and this one is the first to be open to a much larger audience. To be complete, I would also need to mention the expert group that is closely related to this project, to this work package at least, which is the Geological Mapping Modeling Expert Group of the Euro GeoSurvey organization. So in terms of program, yesterday afternoon, we had a very interesting session about 3D visualization tools, visualization of geological models, but more generally subsurface objects, let's say. This morning is dedicated to interpolation and geological modeling methods. And this afternoon, we'll talk about new geological modeling methods. Obviously, the boundaries between the sessions are not very tight. I don't remember the word in English, étanche. Anyway, there are cross topics across different sessions. In terms of organizations, a few words. The good thing with webinars is you don't have to tell people where the toilets are, what is the Wi-Fi connection, because you're supposed to have one. But I would like to give big thanks to all the speakers who accepted to present their work, because it's not always very funny to speak in front of your screen compared to a real audience. Well, I mean real physical audience. I have to mention too that the workshop is recorded. So unless one of the speakers does not want to, all of the workshop will be recorded. It's not decided yet how and if we will disseminate the recordings. Obviously, we will ask for the permission of all speakers. Please try to stick to the allocated time slots as closely as possible. The idea is that we have a program and participants can join when they want and attend the talks they are most interested in. So try not to make too much of a surprise, changing all the program schedules. We have planned breaks to try to catch up. We were running late. And we also have discussion slots. So you can ask questions to speaker using the dedicated tool. It should appear as something like that on the top of your screen, maybe question and answer in English. I must confess too that I had problems configuring the GUI to English, so I don't know how it looks on your side. I hope that everything was translated by Microsoft Teams, but it does not seem to work perfectly. You can use the chat to react loosely, but politely, obviously. And last point, that we are still familiarizing with the webinar system, so thank you in advance for your indulgence. We try to make our best. Nicola is watching the chat if there are questions, and we will ask questions to the speakers. A few words about the program. This is my last slide. We have two parts this morning. The first one is dedicated to already existing geomodeling framework. So we will have Lachlan from Australia. Thank you for connecting so late, Lachlan. We will introduce the loop structural framework. Then we will have a talk by Miguel and Florian from Terraenigma and the University of Aachen about GamePy. And finally, we will end this first part with the talk from Andrea Bistacchi from Milano about the tool P0. And then we will have a discussion about open source initiatives and existing trends in geological modeling. Then in the second part, we will have a session starting with a presentation of the GSEU library from MinParis with Fabien Hors and Didier Renard, which is a geostatistical library. We will then show you something that we are trying to develop at BRGM about trying to combine different geological modeling algorithms into QGIS and try to use QGIS as an operational modeling tool inside the survey. And finally, we will end by a reflection talk by Timothy Kiersey from BGS about different type of modeling, and that should be a perfect introduction to a discussion about how we can do hybrid geological models. And we will try to wrap up and finish on time at 12. And I thank you very much. And then the first speaker is Lachlan. So Lachlan, the floor is yours if you want to share your screen and start your talk.
Yep. Can you see that now?
Perfect on our side.
Cool. All right. Well, thank you for the invitation. It's nice to be able to give a presentation to Europe without having to spend 20 hours on it or more on a plane. So it's better. Just before I start, I would like to mention that we're running a 3D modeling conference next year in Fremantle in Western Australia. So it is a long time on a plane to come from Europe, but it is a really nice place. And I think the conference will be really interesting, being able to discuss different modeling methods and applications. And it's aiming to be more than just a loop focus. We'd like to see people from all sides of the equation, people using the models and developing algorithms. So what I want to talk about today is Loop, but in the 3D modeling framework. So the Loop project has various aspects with going from deconstructing maps, managing knowledge, geophysical inversions, uncertainty mapping and risk mitigation, and also the geological modeling side of things. So I'll focus on the geological modeling, and that is in Loop Structural. So Loop Structural is an open source Python library that I've developed over the last 5 years, and it's come from work that I did during my PhD, work that Gautier Laurent did during a postdoc at Monash, and some other algorithms that have been developed by people such as like the Ring team with Guillaume Cohen. The way that we've developed loop structural is to make it as agnostic to the actual interpolation algorithms and the modeling method as we can. In a way, the eventual aim would be to have something that's like scikit for geomodeling, where you can plug in different parts of the algorithm and not have to rewrite the boilerplate code. And so at the moment, we can interchange different interpolation algorithms. So I've got discrete interpolation algorithms using tetrahedral meshes or Cartesian grids. Then we can use the Surfy package that Mike Hillier wrote in 2014, and that with some Python bindings, we can actually call Surfy from within loop structural and use that to interpolate the surfaces. And I think it will be easy to integrate new methods like the stuff that Mike will be talking about later today. I probably won't be watching, but for all of you that are still able to. One of the really important parts for us with Loop is to be able to characterize structural objects. So talking about folds, faults, intrusions, and being able to do this in a way that makes sense to a structural geologist. So being sort of a structural geologist by training, when I first found out about 3D modeling, and you couldn't integrate overprinting relationships very easily into the modeling framework, that was something that we focused on trying to make Loop able to do. And so along with that, we want to be able to export all of our models into various formats, interrogate the model in Python, and integrate the model into different workflows. And I'll show you some examples of that at the end of the talk. Just a note that we are working on some user interfaces for the library at the moment. So we've got a QGIS plugin that we've been developing, and also there's a JavaScript web app that we are hoping will be released in early 2025. So if you are interested in using Loop Structural, it is easy to install. You can pip install Loop Structural, or you can install it from Conda. The base Loop Structural without any of the visualization and export only depends on some of the basic Python libraries like NumPy, Pandas, scikit-learn, scikit-image. So it's really light and shouldn't have any troubles installing with dependencies. And if you want the visualization tools and being able to export into different formats, you can install with the all flag, and that will get all of the dependencies. When we're talking about implicit modeling, I'm talking about making structural models. So really what I'm trying to characterize is the geometry of objects. So whether that be the geometry of a contact between geological units, form surfaces, fault surfaces, and things like that. So when we are doing this, the input data sets that we would have, so in this case, we've got two folded layers, and our input data sets could be observations of the location of the contact, so these black and orange points, and those black and orange points are assigned to a particular geological unit. And one way we can constrain that is we can actually say we're looking from a reference value of either the black unit or let's say the black unit, and we say that that's 0. And then we know the thicknesses of the unit. So we might say that orange, the distance between black and orange is 10 meters. And so we assign a scalar value to those orange points, and we can interpolate a sign distance field that will measure the distance from or to that black surface anywhere in our model. And we can also integrate gradient constraints, so that the strike and dip of our bedding or our geological unit when we see it, or we can integrate tangent constraints, which are saying that we know a part of the gradient at that location, or we may not know the direction of the gradient. And another way of constraining it is actually to say, well, we don't know what the thicknesses are, but we know these are two separate units, so they should have two different values, but all of the points along the orange unit should have the same value, and all of the points along the black unit should have the same value. So they're two alternative ways of actually parameterizing our model. And we can choose between those two when we're using Loop Structural, just in the way that the input data is recognized by the modeling algorithm. To build a implicit model or to interpolate a scalar field, we can do that with a few lines of code. So here, most of the code is actually just importing the data, setting the variables for the bounding box of the model. The actual interpolation is happening in this model.create and add foliation, and it's assigning the data that's associated with the S0 flag to that feature. And then we can plot the feature in line, and we can interrogate that model. So I think you don't need to be an expert in Python to be able to use loop structural, and there you can take any of the examples and modify them as you see fit. So I think it's usable at the moment for people if they want to give it a go. Now, the structural frames are the key sort of feature that we use for modeling folds, faults, intrusions. And so a structural frame is a new coordinate system that we characterize. So we start off with the major structural feature, which is the object that the geologist would characterize when they're in the field and they're looking at a structure. So for a fold, it's the axial surface of the fold, or the axial foliation. It's the first thing that we're looking for. For a fold, we're looking for the fold surface. And so this is the first coordinate, and we can define that object relative to that coordinate, and then we can characterize another coordinate, which is the structural direction. So we have the fold axis or the fault slip direction, and then if it's required, we can build another coordinate that could describe another element of that object. So for example, in faults, this is the fault extent. So we're basically characterizing the distance to the fault surface being that major structural feature, the distance along the displacement vector, which is our fault slip direction, and then the extent, which could be the map view if we're looking at a fault with a vertical dip, a slip direction, sorry. So using the structural frame, we can actually parameterize our structural elements in the model. So for, oops, oh no, sorry. So for faults, what we do is we actually unfault the model. So we apply that structural frame to characterize where the displacement should be occurring in the model. We then can describe a vector field, which is the fault displacement, and that's parameterized by, if we want our displacement to decrease as we go away from the fault surface, by a function that describes that. And then we effectively unfault the data points that we use for modeling using that kinematic description, and then we can interpolate the faulted surface in that frame, and then our final model can be evaluated by applying that fault operator when we evaluate the value of that scalar field. So we can parameterize the fault by various different geologically meaningful parameters, like the fault center, the aspect ratio of the fault ellipsoid, the dip of the fault, the slip vector of the fault, or if we have observations of these in the field. And so we have a parametric way of describing these geological objects for faults. For folds, we can apply a similar type of idea. So we have our fold frame, which is defined by this vector field here. So we have the red vector defining that major structural feature. So that's the distance to the axial surface of the fold, or a measurement along that field. Then we've got the black vector, which is the fold axis direction field, and then the blue vector, which is orthogonal to both of those. And then if we know the rotation, these two parameters, which are the rotation angles of the fold, which describe firstly what the fold axis would be locally. So if we rotate that y vector by the fold axis rotation angle, we get the local orientation of the fold axis, and then we can rotate that plane defined by the fold axis and the z vector by the fold limb rotation angle around the fold axis, and that gives us the local orientation of the folded surface. And we can use those constraints in our modeling to model folded surfaces. So we can actually parameterize our folds by in the fold frame and apply these rotation angles to interpolate folded geometries. And we can apply this approach in a time-aware way, where we start by modeling, same as the way that geologists would produce a map, in starting with the most recent events, understanding what effect they have on the rest of the geometries, and building the interpretation up. So you start by modeling. In this case, we've got two folds, so three foliations. So we've got the S2. We characterize the geometry of our F1 folding by looking at how S1 varies relative to that S2 frame. We then interpolate our S1 field, and we can do the same thing with our bedding measurements, characterize the geometry of our F1 fold. In this case, we've got a recumbent fold that's been refolded by the lower amplitude, shorter wavelength F2 folds, and you can see the refolded fold that we get at the end. And so these parameters can be applied in combination with the faults, and those parameters can have uncertainty values associated with them as well. So we can actually explore how that our understanding of those parameters actually impacts the resulting geometries. For loop, one of the other key aspects we have is this workflow of going from a map to a geological model that we call map to loop. So we basically deconstruct our map into the important components that are required for the model. So we extract out the basal contacts and the fault traces. So in this case, we have these younger sedimentary units that are overlaying the folded stratigraphy, and then the folded stratigraphy is faulted. So we can extract out that information, build a stratigraphic column, and apply our understanding of the thicknesses, and to calculate those the data points that are required to build the model, or the constraints that are required to build the model. And so we've wrapped this up into a library called Map to Loop, and this library allows us to deconstruct a geological map, picking out the basal contacts, picking out the stratigraphic order, identifying fault traces, picking out the fault displacements, and then building up this input data set for loop structural. Now, we've been talking about Map to Loop for a long time, and probably a lot of people have seen these slides, but over the past few years, we've actually been spending a lot of time in trying to make the algorithms more robust and building the framework to be more reliable. So I think this week we actually released 3.2 for Map to Loop, which is reasonably good. It actually requires more user input in defining the constraints for the model, but that user input is really important in understanding what you're trying to model. So rather than giving you a bad model without telling you that it hasn't been able to calculate something, it will require you to input the unknown data. So if you can't calculate the thickness of something, it will return a null value, and you actually have to input that yourself as a geologist. And that can be really important in actually making models of areas that aren't as nice as the Hammersley Basin, which has the really nice stratigraphy. So these are the examples of the augmented data that we calculate from Map to Loop. And then this can be used to build a geological model. And then we can compare that model. So we're comparing the traces of the basal contacts with the unit that was evaluated on the DTM using the stratigraphic column lookup that we'd have for the scalar field. So basically assigning different values of that scalar field to a particular geological unit. And it's reasonably close, but there are some differences. And that's sort of to be expected, because we're doing a pretty bad job at characterizing the fault displacement. So we have a lot of uncertainty around there. So that's something that we need to look into to actually build a better model. And the thicknesses of the units were probably not estimated that well in the most part. So the next thing that, so this is more of a development that we've been looking into in loop structural, rather than just talking about what it can do, is how do we integrate inequality constraints? So when dealing with mine data sets or fault-bounded units on a map, there aren't contacts. We can't just put in a contact value to build our structural model. And so you may have a blind drill hole that it doesn't show any changes in stratigraphy, but that fact that you recorded the same stratigraphy down the drill hole is actually really important in characterizing the geometry. So we need to be able to input that data, but without having to infer the location of the contact manually. And so inequality constraints are a really good way of doing this. So if we start with one type of inequality constraint, which is basically just to say at this location, the scalar field value should be less than, so it might be there, you're saying that it should be less than -10 because we're away from that zero surface. And those constraints are good if you know the thickness values of the units, and they're fairly cheap to apply computationally. Or a more expensive approach is to say that we have these pairs of observations. So we've got the black units, and we know that the difference between the black units, the black unit and every point of origin should be greater than 0. And we can apply all of these constraints into our interpolation matrix, and we end up with a way of constraining the geometry quite nicely. The problem is the number of constraints can expand quite quickly, and you end up with a very expensive system to solve. So we use the ADMM algorithm for solving the inequality constraints, which is Reasonably nice to fit into a discrete, like a least squares based solver, because it has a similar, it's not a hard constraint. So the inequality constraints are fitted as well as they can be given the ADMM weight that you give it. And you have only a certain number of iterations that the solver will apply. So this is just an example of applying the pairwise constraints to a test case. So I built a model from a test data set that we've been using quite a lot. It's from northwestern Australia. Geomodelling prepared it for a interpolation comparison paper we're working on. And we basically sampled some drill holes. So we built an original model, then sampled the drill holes, desurveyed the points and identified where the contacts, or what the unit would be along the drill hole, and then identified where the contacts between where the drill hole changes in the lithology ID, and used those as constraints into the system. So we ended up with 50,000 constraints in the system, and we can solve that in about 2 minutes. Just on a standard computer, like a decent laptop, but nothing special. So it's not running on the cloud. It's not using GPU. I think it was only using a single CPU solver. So it definitely could be improved. And this is the resulting model you get. So in this model, we haven't used any contact locations, only that the constraint is that the yellow points must be below the green points and so on. And there are no orientation data set included in there, but we can add those in. The last two things that I want to talk about is where we're going with actually using the loop models for something else. So there's a PhD student at University of Western Australia. So it's actually, she's not associated with Loop. She just found Loop on GitHub and decided that she wanted to try and use it to build hydrogeology models, and then looking at the uncertainty in so looking at fault displacement uncertainties and looking at where you don't know the outcropping location of a unit. So seeing how much effect that would have on the resulting hydrogeology simulation. And it has a fairly large effect. So because we're changing the connectivity of the units, when using ModFlow, you end up with quite a significant displacement difference. This is the example using the fault displacements, and we're looking at just a few iterations of different models. So this is sample 0, 120, and 200, and looking at the head distribution. So the height of the hydrogeological head, and then as a uncertainty metric, we can look at the standard deviation of the head for those simulations. And you can see that there are some, so as we move across into the area where the uncertainty is, you get a really high standard deviation in that head, and where the fault displacement is the same thing. So what it means is just doing an uncertainty grid search in your hydrogeology models maybe isn't enough, and we actually need to change that geological framework. The last thing, and I'll just go quickly, is we've added a link to MMG tools to actually modify tetrahedral meshes using the loop structural implicit model. So this is just an example from one of our from that refolded model, where we can add in the contacts between the units as a surface in that tetrahedral mesh. So this means that we can then plug those meshes into numerical solvers such as Underworld and solve whatever partial differential equations you want. So I'll leave it there because I think I've gone over time. And yeah, there's the summary. So thanks for listening.
Thank you, Lachlan. You're perfectly on time.
Cool.
Very, very interesting. A lot of information. We have time for a quick first question of the morning. Is someone has drink enough coffee? How we switch to Florian and Miguel? Yeah, il n'y a pas de question? No question? Okay, well, let's switch to the next of them. Florian, Miguel. I don't know who's talking. Florian.
Yes, I'm talking. I hope you can see me already. Presentation is running.
Yep.
No? Okay. So thanks a lot, first of all, for the invitation. Great to be here virtually and to present a bit what we've been working on in the framework of GemPy. in terms of open source geomodeling. So I'm speaking here. Miguel is here also in the presentation, and of course there's a whole team of people behind it. But let's jump into it. So GenPy, what is GenPy about? Well, I could talk about models being created with GenPy. Just to give you a bit of an insight, obviously we talk about geological modeling, and we see here an example of a model in the Molasse triangle zone. So this is alpine foreland. This is a model here in a basin setting in the Aargau in Switzerland. Another model, North Sea here. So offshore, typical oil or actually CO2 sequestration prospect. And here an example of one of the models we've been creating for a geothermal study, also on a scale of tens of kilometers. But actually, well, you know how these models look like. So what I want to talk about today is rather, instead of the modeling itself, the entire framework, which is set up around GenPy as an open source geomodeling tool. And you can see here a bit of the view, so giving us the guidance a bit through the presentation. We start at the very core of what is behind GenPy in a couple of words and slides. And this is the GenPy engine. So what is the engine? Well, you know, if you ask DALL-E, favorite AI tools for image creations, or your other choice, what a geological modeling engine looks like. Looks a bit like what we see here. Not sure if this is really helpful. Looks a bit like a steampunk style geomodel generation. Obviously, what we talk about is actually a lot simpler, maybe. It's in the engine room. GenPy is 3D geological modeling based on implicit surface representations, so similar to what we've seen in loop structural and similar to what we have in many of the modern geomodeling packages. It's Python-based, meaning that as a front end in the end, as the user, you are writing Python code. Underneath, it also is based on very efficient implementations. A lot of focus has been on building up a robust data structure based on the subsurface package. We'll get to this in a minute. And at the moment, the main interpolator is universal co-kriging. This is based on a theory, Lajeunesse et al. 1997, which is also implemented in GeoModeler. And the point is here that you can use surface points and orientation values directly to create a model. What does this look like? The interpolator itself really has minimal dependencies, which is one of the core features of the new developments. So you take an input, as you can see here. We have surface points, we have orientation values shown here with these arrows. And the main point is actually that creating a model out of these points is as simple as typing basically one command in Python. The point is here, minimal dependencies, only NumPy, which means that it will install on any system very easily. It's very robust, it's very efficient, and the foundation basically of everything that I will show in the following. Just as a small comment, it's so minimal in terms of its the requirements, the dependency, that it's easy to run even in a Google Colab notebook. So you can run GenPy even with the 3D visualization you see here. Completely online. You don't even have to install it on your local machine. So there have been new developments in GenPy. Maybe some of you tried running or installing GenPy before, and there was always the difficulty with a machine learning package that we used to use called Theano, just been deprecated. So there's a new version in GenPy out now, version 3. All credits here to Miguel in the talk, who took a lot of time and care to completely refactor the entire core basis of GenPy with a focus on these minimal dependencies, on high efficiency, and on robustness. And now we benefit a lot from this. So GenPy 3 is the new de facto version. Main focus was also on a clear internal structure to ensure long-term curation. So there's now a clear separation between basically this engine part and the things I'll talk about in the following, which we hope will also keep this code maintainable for the future, basically. Technical developments. So we worked a lot on other types of technical developments like dual contouring and octree refinement. What do I mean with this? Well, you look here, basically, you can think of a complex model. Now, this is very small now, but think of a huge model with many, many cells in which you would like to know the geology. Then if you want to get here from a very coarse model, like this edge basically, to a higher resolution, you have to refine everywhere. Octree refinement basically only refines where you need it. As you can see here, so now the model is refined basically only in this area of our domain where we actually have an interface. This leads to a very efficient implementation of the surface extraction and also enables a higher scalability of the modeling methods for more complex and large-scale models, potentially on the scale of entire countries, let's say. Another type of development that has been happening in recent couple of months, let's say, is also that we are extending this engine basically with other types of interpolators. Lachlan already mentioned the code GeoINR by Michael Ye. We extended this actually in an own work to include also faults. So what you see here in the top right is this Gullfax model using this new machine learning implementation, GeoINR. And we're also working on different approaches to couple models across hierarchies. So basically to have geological models as the frame, surface models as the frame, and then to fill basically the space with, for example, geostatistical simulations. So this is in the engine of GemPy, we can say. Yeah, and one more point is also that we work on sparse matrix calculations, which will also ensure like a higher efficiency, especially for large-scale models. There's also an approach to work on what is called local anisotropies. Very briefly here, the idea is that, of course, when you are, this is a bit of a schematic picture here, but if you think of the scale of an entire orogeny or entire country, you have areas where you have high anisotropy, so high changes, high structural changes, high complexity, and other areas in basins where your geology is, I don't know, flat sedimentary layers. And typical modeling algorithms always struggle with this type of variation. So we've working quite a bit on making this a bit more flexible to allow for areas with different types of complexity, let's say. Here's a paper that is currently in review where we do this on the basis of variational Gaussian processes. Small detail and look out. The next thing is obviously once you have your model, you have your engine doing the work, you want to visualize the model that you have. And in the GemPy framework, at the base, we use matplotlib. I'm sure many of you who at least work also in with a bit of Python that you know these methods. So it's basically simple plots directly in Python, but you can get nice visualizations. Obviously, what we typically want are 3D representations. And we see here an example using PyVista. This is our basically de facto standard visualization tool. It's also an open source toolkit based on the VTK library and allows for direct actually manipulation of models and visualization in 3D. Okay, but really exciting is in the GemPy framework, the possibility to extend what the code itself can do with links to other packages. And this is really where I'm going to come back to this point where the power of open source comes into play. So we have several packages where we have really close links to in the form of, you can say, plugins, really. One is on the level of geographic data. So we have GemGIS, an own package, which actually does a lot of processing of geographic data and ensures a link to, for example, QGIS, ArcGIS, and so on. We have a strong link to the subsurface library, another Python library, which we use, for example, to load borehole data, cross sections, and so on. We have a link to machine learning frameworks and to AI tools. And let me show you a bit what this looks like. Well, machine learning links are most at the core when we talk about probabilistic geomodeling. Lachlan showed this very nicely with these concepts of uncertainty representations. So this has been at the core. I mean, those of you who know my work, has been at the core of my scientific work for, I don't know, more than 10 years now. And we implemented this in the core of GemPy in the first version already. And now we changed this to different types of machine learning frameworks like TensorFlow and PyTorch, which are now the more, let's say, modern types. And why do we do that? Well, as you see it here, so here we have a GemPy model in the 2D section. Above this, you see a gravity anomaly. And obviously, when we change the model, the anomaly changes. And if we have measurements in the field, we can then use this to constrain our geological models. Okay, that's a bit of a side note. Another development we've been working on more recently are links to AI tools. And well, I'm sure everyone has heard of, and probably all of you have used ChatGPT, but maybe you also know that behind these large language models, the front ends, these chat interfaces, there are basically these large language models, foundation models, which you can also access through a programming interface, an API. And we've been testing different approaches, some based on OpenAI's. This is the company behind ChatGPT. And there are also some types of frameworks like LangChain, which allow you to interact with these models on a Python level, basically. And we've done quite some work on exporting information into databases, which allows you to retrieve this information flexibly with these AI tools. So this is a bit more technical detail. Let me show you what this means. So ideally, possible applications are in model generation, what we call maybe image to model. So the idea that you actually have an image and you create a model from this, and fitting models to geological knowledge. Let me show you what I mean with a small example here. So this is a simple GEMPI geological modeling assistant that we created, where you can type in a question. It will retrieve context, and as you will see in a second, this is actual context relating to models that were generated and that are stored on our website, even including the link. So if you want to see where this is coming from, we can actually click on this view source, and it takes you to the website where this information is stored, so to the geological model as a test case, basically. So it's retrieving this information, and then it's generating an answer, which is based on our question. And in this case, it gives us a code to create a geological model with 3 layers cut by a normal fault. At the moment, no guarantee that this will work. So we actually also, there's still this aspect of hallucination in code, but we are extending this with more information to make sure that it actually fits. Another thing you can do is you can ask questions when you have problems or maybe suspect bugs. We actually fed this model with the entire GitHub issues of all of our issues on the GEMPI website, and it retrieves this information and generates answers based on answers that were given previously in our discussion boards and issues, for example. And it takes you also with the links to these to this information, which is then basically online, and you can continue there, ask questions, or hopefully get an answer. That's one thing. Another thing we've been working on, what I said, this structural geology image analysis app. This is a really prototype, but the idea that you basically upload, for example, a sketch, or you think of also an image, it analyzes the image and gives you code that you can actually use as an input for geological modeling. So you could actually, this is in JSON, so we're writing basically as an input from JSON to GEMPI. It analyzes this picture, identifies that the layers are called layer 1, layer 2, layer 3, and so on, and that this is actually an anticline. So, I mean, these are, let's say, first steps, but I'm sure all of you have a bit more tested these methods. This is evolving rapidly, so we're actually quite excited to see where this can take us in the future. Okay, let's go on to the next, basically, level of our shells, and this is the integration of all these tools with more software that is out there, and I will focus on 2 parts here, Liquid Earth 1. Just mentioning here that there's also a strong link to QGIS. We have links to Blender, which I will show quickly. PyGimli, which is a geophysics modeling package, and Moose, high-performance computing for really sophisticated process simulations, which I will not go into further today. But let me show you a bit the link to Liquid Earth and Blender. So Liquid Earth is a software that we create in the company Terranigma Solutions. This is a startup formed out of our previous work, the Institute. Miguel also here is one of the core people also in this company. And we have the software Liquid Earth 1, which is really meant as basically a tool for visualization, collaboration, and presentation for multiple users, basically in 3D space. And what does this look like? So it allows you to do multi-device collaboration. So you can basically interact with your models. You can see here a model created with GEMPI. You can see multiple people working with these models or investigating these models basically in 3D space. You can actually discuss. There's, in the meantime, there's also like an interface, a chat interface inside the software, so you can speak with each other and talk to each other. And you can collaborate, for example, link this to outcrop data and so on. The nice thing is when you go back to GEMPI, It actually has a direct API for data integration. So you can get an API key if you have a liquid earth license. And it's as simple as this, basically, to take one of your models that you create with GenPy, add this code to your Python code, and it will directly create a so-called space. So basically a 3D frame for your model in liquid earth, and create this model in liquid earth for you. And then you can directly start interpolating and so on. Interrogating, showing, and so on. Another type of link is to Blender. For those of you who know this, Blender is an amazing software as well, like an open source tool for really high quality visualizations and high quality rendering. You can see here an example of this model I showed before in the area of Aachen. At the top, you can actually see the landscape and topography map. And if you look inside this model, you can see this nice folded layer, basically the cross-cutting faults, which is relevant for us for purpose of geothermal energy. The point is, of course, you can create also really high quality movies of your 3D geological models, which are top level quality, I would say. There are other developments using, for example, K3D for visualizing models directly in the browser, JavaScript and leaf map and so on, just to mention this here. Okay. In all, bringing this together, basically one of the important points is that this is a framework, and the framework also lives from an active community, and we are really happy. Oh, I'm sorry about these. Windows messed up my logos. Anyway, we are really happy about this development in recent times, so that we have our code basically on GitHub. This is one of the standard platforms for open source platforms. And you can see actually that we broke the barrier of 1,000 stars. So for those who know what this means, basically these are recognitions by the community to say they like this code. And this has been a tremendous development since you see this 2018. It's continuing to rise. So that's fantastic to see this interaction with the community. We also support this interaction as much as we can. If you have questions, for example, you can go to GenPy. You can ask if you have an issue. Let's say you see a problem with maybe a bug, a suspected bug. You can put this online here. We have discussions, which can really be as simple as saying, I need help creating a model. Can you help me? And we have multiple of our group here joining these discussions as well as we can to support you in these, to support the community and also to build up this community further. There's also a very detailed documentation website, and I would like to add this specifically. There is now a nice tutorial series online, just started last week on LinkedIn and YouTube. So if you want to, try it out, at the moment is a perfect time. Go to our website or look in LinkedIn or YouTube for GenPy tutorial, and you will be guided really step by step through creating models with GenPy. Well, GenPy in science, there's also a lot of publication. This is now a bit more my university hat. I'd like to add also that actually a lot of funding has gone already in projects around GenPy and in building up this framework, including already funding from TNO, BGE, BGR. And there's a lot more in ongoing projects. Now, in the interest of time, I will skip forward a bit through those. So we have really exciting work in a project called BBGeo, where we look at different interpolators. So Simon mentioned this before also as a work that is done at BRGM. We have this project called Vector, where we link also geological modeling to many other types of developments like full tensor, gravity, gradiometry. So if you're interested, ask me about this later. Because one thing I would like to mention is this idea that we've been working on for quite a while to actually extend GenPy from this open source modeling tool to a foundation. You see this here sketched a bit. We have the vision that we get universities, small industry, geological surveys ideally involved in developing core aspects of GenPy further. Why? Well, some final thoughts here. I hope I could show you that basically there's a huge potential in open source tools. Coding literacy is rising, so there are more and more people who can code at least a little bit of Python with the help of GPT. This is actually really easy now. With these AI tools, they're here to stay, I would say. So they're becoming an integral part of our modeling frameworks. Writing code itself is easy, but maintaining a good code, this is difficult. And reproducibility and stability is key. So it's really a challenge for long-term code development, and this is why we require to keep this project in this scale running. We require external support beyond what we can do at universities. And this is my call to you as a final mention here. Simon mentioned that we should also be a bit more, let's say, provocative in what we say. So we think this is a collaborative solution, but we need you on board, we need geological surveys on board, we need companies on board to help us shape the future of GEMPI and open source geological modeling. We are just looking at creating an initial board of the foundation, so perfect time to join and join the future, shape the future of GEMPI and open source modeling. And with this, in the meantime, look at our maybe tutorials, and thank you for the attention.
Thank you, Florian.
So now, but I'm really now at the limit of the time.
No, that's perfect. One question maybe?
Or we keep the discussion for later.
Yeah, maybe if it's short.
Otherwise, just ask in the chat. I'm also happy to answer there if someone has questions.
Can I create an export from GEMPI to import into Civil 3D?
Civil, wait, can I see the question? What is that?
That's wow.
Civil 3D. I don't know the software. You have to tell me a bit more about the modeling formats.
Anyway, you can answer the question at any time in the question and answer section.
If you type more questions, I can. Yeah, I'm quite.
Yeah, let's switch to Andreas, and we'll come back to a discussion session later. Thank you, Florian. Then Andrea, I don't know if.
Hello, thank you.
Yeah.
Good morning, everybody. I'm sharing the screen. Do you see it?
We see your screen, yeah.
Yeah, so here we are. Okay, so we are discussing now P0, another open source project. We have been developing since 2020, actually, with these people mainly, plus some others that are mentioned on the GitHub site, and I thank them all very much. Okay, the first step we started from is at the time in 2020, there was an increasing number of libraries aimed at 3D geological modeling, including the two we have already seen. So Loop Structural and GEMPI, obviously, that are the most important. But in 2020, we were completely missing a graphical user interface to interact with these tools. And so we started thinking about what we need to do to build 3D geological models in practice with application problems. And we went back to the original definition of geomodeling by Jean-Laurent Mallet that says that, okay, it is important to model in a unified way the topology, geometry, and physical properties of all geological objects, but it is also important to take into account any type of data related to objects. So it is fundamental to be able to import any kind of data like seismics, wells, digital elevation models, meshes, well, let's see. Okay, borrow 2D and 3D images, use different kind of meshes, and obviously we need to be able to use any kind of geometrical topological entities that could be useful to build the model or also to export the model. The question that just came a minute ago about exporting into Civil 3D is something that was originally included in our project, because actually we are able with a dedicated workflow to export to BIM, so to what engineers use to develop their projects for instance, underground facilities, tunnels, and so on. Okay, and so on the other hand, the idea was to go in a completely open source direction. using our background to build a model that was particularly aimed at complex deformation, for instance, in mountain belts. This is what I've been doing since I was a very young geologist working in the Alps. And another aim was to open in this kind of complex structural environment, tunneling, 3D modeling to tunneling, hydrogeology, landslides, engineering geology, etc. That most of the time happen to be developed in complex areas like the one in the background. Another idea was to provide a platform for rapid testing of new modeling algorithms, and we will see that we are able to do this thanks to a deep integration with NumPy that allows linking with many different modeling libraries. Since the beginning, we invested a lot in developing a graphical user interface that is aimed at classical geologists in a way. So with classical tools like for, I don't know, stereoplots, for instance, or cross sections that can be easily reconstructed by in a classical workflow. And last but not least, we wanted to manage uncertainty. This came as a specific request from engineers with whom we started collaborating since the beginning, because they know they're very interested in knowing what happens to your geological model as you add more data along the workflow. So, for instance, with this way, we can record how the model is improved as we add more data and that we change the scenario, the interpretation scenario. Okay. These are the libraries that the main libraries that we use. Then we use some more, and through whom we are very much indebted. At the very core of P0, we have BTK that is used for visualization and managing all 3D entities. And we use quite a lot of the interface between BTK and NumPy that makes it very easy to integrate any numerical calculation in a Python environment. And from this to pandas and to loop, that is the library that was previously presented by Lachlan, that we use for implicit modeling. And then we use many other tools like Shapely, that is the same 2D geometrical and topological library used in QGIS. We use it to perform some for some tool in 2D views, like in map or in cross-section views. And we use PyVista, which is very handy for some visualization tasks, XRA to import and export data, and so on, Matplotlib for many kind of plotting and so on. This is the interface at the moment. So we have different panels. All these windows can be resized. Here on the top left, we have a sort of table with different kind of objects. We will see them live in a minute. Basically, we have geological, fluid objects, background objects, digital elevation models, images, meshes, cross-sections, wells, and so on. Down here, we have the geological legend, and then we have another legend for properties that are shown in many views. And we will see that the central panel is taken by this view that can be either a 3D view or multiple 3D views, multiple cross-sections, map views. We can have different kind of plots, stereoplots, and so on here. And to the right, we have this panel that is used to activate and activate objects in the different views. And what is nice, we spent some time redesigning the interface in the last year. It was very boring, actually, but we like it now. Okay, going back to some technicality, these are more or less all the basic objects and basic topologies we can use. This comes directly from BTK that enables using any kind of standard topological object like point clouds, polylines, triangles, and so triangulated surfaces, and different kind of 3D meshes or grids. We are not using all of these objects at the moment, but adding some more in case we need them is very easy actually, because we are using BTK as a background for every purpose here. And so, for instance, we have different kind of meshes like tetrahedral meshes or regular grids with box sets. But in case we need to add something like a pillar grid like this, it will be quite easy. We haven't done that yet because we don't have the necessity, but it's easy. And we can use different kind of explicit interpolation algorithms, like, for instance, standard Delaunay triangulation and many others. That I mean, they are a bit old, but sometimes they are still useful, particularly when you want to test very quickly some hypotheses, or maybe you have some simple model where they are enough. And we use implicit interpolation. We have heard a lot about implicit interpolation, so I will skip here. Basically, we are using loop structural that was linked very easily in our environment through NumPy and Pandas. And okay, and just to go to what we are still working on the theoretical side, some thing we are working on at the moment is to be able to completely implement finite folds and wide folds. That are always a big problem in 3D modeling. And by the way, I've seen some new tools on both previous libraries that are very interesting in this sense at the moment. And regarding uncertainty, what we are doing at the moment is mainly, Florian will know very well this plot, by the way, that is very successful. We are mainly using a sort of first order uncertainty in a way that allows transparently manage different scenarios. So if we have different scenarios, we can label them and compare them within the same model, the same interface. And we found that this is very interesting, for instance, for people doing downstream applications, like, I don't know, engineers designing a tunnel. They want to know where the higher uncertainty is and what would be the value added by, I don't know, for instance, a new borehole drill exactly here. Then second order uncertainty, we are working on that on some different project. And actually, it is a very old story. This is some reasoning we made a lot of years ago in a project that dealt with a very deep tunnel in the Alps. And at some point we will include also that actually it's not that complicated. It's thanks to the fact that we can manage all calculation with NumPy. So I conclude with a sort of comparison between P0 and commercial codes. I have not included PyVista and Loop in this comparison because I was just considering codes that present a standard graphical user interface, but also because they are subject to such a fast evolution that is impossible to catch up. So the idea is, first of all, to compare the main application of this software. Most of them are mainly aimed at oil and gas applications, and we know that, for instance, it's almost impossible to use petrol out of a standard oil and gas environment, because for instance, if you tried to import a digital elevation model in petrol, you know what I mean. The license here is always proprietary, and what is worse in many cases is that the documentation is a sort of black box for most of this software, and this means, the only commercial code that is really documented in papers is CAD. You have very good idea of what it does, just this one. And this is an increasing problem, for reproducibility of your results. So this is, in addition to being to the low cost, I think that the main point in open source geomodeling is you can read the code, you can read the papers, and you know what this engine is doing on your data. Regarding interpolation, okay, we do both implicit and explicit interpolation, and the other codes do only some of them do both. Regarding complex faults, probably at the moment in commercial codes, the best management of complex faults or wire faults or finite faults is still the one you have in school of CAD. Okay, with the help of people who are developing very good libraries, we are catching up. A transparent management of scenarios, as far as I know, is viable over the School of CAD. A workflow to export to BIM software is only viable in Leapfrog. And we also have the tools for the analysis of digital outcrop models in the form of point clouds with several 100 million points and so on, that came out as a sort of addition, because actually it came out that VDK is so efficient that it also handles very well the digital outcrop models. So what I can do is to, okay, last slide. If you want to learn some more, the best thing is to install it and use it. This is the GitHub repository where you can find everything. Just a note at the moment we are at the end of this refactoring regarding the graphical user interface. So in case you want to try it today or tomorrow, just write an email, because we should give you a couple of details that are important. In January, it will be everything straightforward, because basically we are updating the master branch with the branch where we did the refactoring of the graphical user interface. And okay, so what I can show you is, for instance, the interface, and I think you see it. Okay, this is a pretty huge model. It's this is around half the Aosta Valley, so it's around 1,600 square kilometers. The digital elevation model here is at 16 meter per pixel resolution, so it's a really huge digital elevation model, and we have like I think 50 or 60 cross sections in this model. And okay, I don't want to go into details of the geology here. That is quite complex. We go from the Mont Blanc here to the Monte Rosa here. So we are all crossing from the elevated domain to the Upper Penninic. And we have big mountains here. This is the Trancomben. This is we have the Matterhorn, but we don't have much time, so I just want to show some other stuff. Let's take a very simple model. So again, the interface here, and if I want, and well, what we spent some time doing was to synchronize every window we have. So for instance, if I draw a new line here, I can define what it is, and let's say this, and this, and I start drawing. And as soon as I finish drawing, I see the line appearing in the other window, and so everything is very, I mean, I like the way it works in this very efficient and nice way. I can change the color and so on. Here I've done something wrong. I put this line on the wrong line and so on. I can go back here very easily. These are all tools that come with VDK. And okay, and last but not least, I want to show you how we managed to implement the implicit interpolation with the loop in our model. So I'm going to a map view here. And the first step in an implicit interpolation workflow is to define a volume where the implicit interpolation is carried out. So I can create a volume here, like from this and this, and okay, I created this new object. The new boundary is here, and I can see it also on the 3D view. It's this box here where I will build my model. Then I go like here, and I would like to select all objects in cross sections. They are this one. They are pretty much like all this one. So I go to interpolation, loop structural interpolation. Now I'm basically, this is possibly the longest time it takes in translating all objects from VTK into the data frame that is used for loop interpolation. Then I select some method, I say yes, I select a resolution for the mesh, and it's going at some point. Okay, finished. So I have some, I can hide this, and I see here the new surfaces that have been interpolated. Yes. These are the new surfaces that are completely contained, obviously, in the box that I have drawn, and I can also look at the implicit surface that was created. That is this one. That is the scalar field that was created. So it's very fast, and this is all thanks to the people like Lachlan who developed Loop. And well, yeah, thank you very much. And I'd like to take any questions. Thank you.
Thank you, Andrea. So we have around 10 to 15 minutes for questions. So Are there any questions in the room? I think that's yes, several questions. I'm going to change my screen. Okay, Zbigniew is really happy that an open source software has a GUI. Congratulations. That's an important point, I guess, when you're targeting very high-level user or geological experts. Another question dedicated to P0. That's the effect of the last talk. When you have a discussion session, questions tend to focus on the last talk, but I have more general questions. Can you also visualize seismic data in P0?
Sorry?
Can you import seismic data?
Yeah.
Yeah.
Yeah, we can import. At the moment, we are merging because we developed at the same time the new graphical user interface and seismics, basically importing SIG-Y. So at the moment, they are still on two separate branches, but we are merging them at the moment. So we have seismics, both 2D and 3D seismics, and we are also able to perform something like auto tracking on the 2D or 3D seismics, thanks to some machine learning algorithm we implemented.
Okay, thank you, Andrea. I think that Jan Franek, you asked to you raised your hands. The idea is rather to just ask your question in the chat, and we will read it. The point is, as we are many of us, if we give the mic to a lot of people, we don't know how to manage it. Waiting for the question from Jan. I had a question. I think that you're all teachers, part-time or full-time teachers in universities, and I was wondering, how do you use teaching to improve the code that you are developing? Because with Geomodeling, we've been teaching geomodeling on the field for 20 years now, and I think the early versions of Geomodeling really benefited from this teaching experience. So, Florian, you wanted to?
Yeah, I can start. So we use it in teaching, both in like theoretical modeling classes. So really for people understanding the basics of modeling, we have one class on modeling theory, let's say, and we use it in field trips. And I think this is similar to what I mean you've done in LS with Geomodeller. We actually also used it in LS already some years ago, and this helps a lot to see how students interact and how they think, how people think. Right, this is definitely the point. So there's quite some interaction, and this, yeah, that helps for sure.
I don't know if Andrea or Lachlan, you want
to... Yeah, we are starting to use P0 for teaching, and this is also very important also for the code. I think that also the others have the same experience, because the students, they are very good in finding bugs. They always use the software in different ways with respect to how you think they should use it. So they take some different path, and every time they get some crash, some unexpected behavior, and this helps very much to find bugs.
Lachlan, do you use it in Monash?
No, I don't do any teaching, and there's no 3D modeling or coding in our geology degree, which is a real shame. It's yeah, no more comment than that.
Okay, I'm a bit surprised. I thought that in Australia there would be. Florian, and students, are they happy with writing scripts, or do you force them to write scripts?
You know, when I started teaching 10 years ago, I had to convince the students that it's a good idea to learn coding. And there was quite a hesitance. In the meantime, I have students coming to my class because they want to learn coding, and they know that this is a skill which will help them get a job, get future work done, basically. And because in the meantime, you have all these tools that help you coding, like also GPT, Copilot, and all these things. So the hurdle is actually really low, a lot lower than it was, let's say, 10, 15 years ago. And I have some of the students, they then end up in LinkedIn with their jobs as, digital change professional for some industry and so on. So this helps a lot, and I think students know this. So this is it's very rare that I have students who tell me I don't need coding in my life.
Okay, it still depends.
Yeah, I
because,
completely agree.
yeah,
I agree. I mean,
Tim?
we've been finding it with our new recruits that they take to coding. You know, it's a second nature to them. And again, as Florian mentioned, it's the democratization of some of these of the large language models that are just making it really open. So you don't even need to know. I mean, I remember when I first started coding, it's, you know, you just spend hours debugging code and it's just a real pain. Now you can throw it in a thing and it will find the missing space or the hanging space or all of those things and just do it out. So it is lowering the bar. So as long as you can understand the logic and you can think it through, you know what you want them to do. Yeah, it's completely democratizing the whole system. It's brilliant.
Yeah.
Yeah. It's a bit frustrating when a student copy paste what ChatGPT gave him, because
Can go wrong. So that's something which you have to learn. It's not
Yeah.
not as simple as copying. You need to still understand
Yeah,
something.
sure.
At least let's wait for GPT-5. Let's see.
Yes. So the question from Jan in the chat is about geophysical data. He was first wondering how to incorporate other geophysical data, not only seismic, but the kind of data that we used in other fields like resistivity profiles, also refraction seismic. So I guess that we can ask all of you three, what is the interaction with geophysical data? And maybe you can give a few words about inversion of geophysical data, because I know that some of you have done some work on this. Don't know who wants to start. Lachlan, the order of the presentations?
Yeah, I can start. So I've been working with Jeremy Giro and he did a Marie Curie fellowship at Ring, and he was integrating loop structural into Tomafast to update the interfaces between geological boundaries for inversion. So that is quite cool. It's still a work in progress. I think he's got another fellowship to do the same thing. So it's obviously something that is appealing. We've looked at other ideas like trying to do localized inversions to actually so where I talk about the structural parameters, to actually understand those parameters from a geophysical point of view. So refining that prior space using geophysics to then feed into a geology model to get a better understanding. And then I guess you can use your standard approach of doing a geophysical inversion on the resulting model, but I'm not convinced that that's that beneficial. Because you don't really change the interfaces that much. But maybe that's my bias. And the other thing you can do with geophysics is have interpretations of the potential field data as an input. Like if you don't have a geological map, you can use that as an input into your 3D modeling.
In our framework, we have this link to, I mean, some geophysics is built in, as I showed. So gravity is built in magnetics already in GemPy. For many others, we use this link to PyGimli, as I mentioned before. We also had some people linking it to SimPack, which is another big open source library for geophysical simulations and modeling. And we work together with Florian Wagner, professor here in Aachen, who has developed one of the core developers of PyGimli. And we actually have running workflows doing what we call model-based inversion. So actually taking your geological model as an input, comparing this to ERT data through this forward simulation, actually adjusting the geological model that you have a valid geological model at the end. And that's working, for example, with ERT. We've applied it with magnetics, seismics. There's ongoing work to link this to with gravity as well, of course. So yeah, that's definitely possible, this combination.
In P0, well, basically, importing any kind of like gridded data is very easy, and I think it's the same for the other codes because we all use NumPy, so it's very easy to import any kind of gridded data set. And actually, the most difficult import was SIGY because it's always non-standard, so you have to deal with, particularly with all the SIGY files that always create some problems. Then we, at the moment, no, we are not dealing with like inversion or some advanced processing of this data. could be done in the future. It's maybe if there is somebody who is interested to interact on that, it could be interesting.
Okay. As the title of the discussion session was also about trends, I noticed that faults still remain challenging problem. I think that they will be there till the end of geological modeling. I don't know, what's your feeling about how much remains to be done on faults modeling? This is the easy question. You know, when you have a geomodeling workshop, you talk about faults or uncertainty. It's always there. Your 1 hour talk.
I maybe can comment a little bit on. So I think that depends on there's one part of faults is actually the scale of the fault that's mapped and trying to put that into the model, and that I think that should be separated from the actual process of modeling the faults. So we're trying to make a model of New South Wales last week, and there's 1 million faults on the map, and you can't make a model of that, obviously. So you need to have some sort of upscaling to have the data set appropriate. Then there's actually integrating the faults into the modeling framework. So our kinematic approach has advantages over doing it in the depth function approach, but it has the downside of requiring more data that people don't collect, and then you've got the uncertainties associated with that. So I think there's going to be a combination of all of the above approaches. Maybe doing stuff like Florian did with, or you've done with the implicit neural representation. Maybe that will solve everything because you can get all the good bits of the different approaches. I don't know. I haven't actually read the paper yet. But.
Yeah, I think so. I mean, faults, as always in these modeling packages, simple fault networks are easy. It gets difficult when we have multiple intersecting faults and so on. And in the current phase, so well, finite faults are possible, infinite faults are possible. Fault networks, depending on the method you use, are a challenge. We've also been working on combining the implicit interpolation methods with explicit representations, where you actually model the faults more explicitly, like you do, for example, in GoCAD. That's possible if you want to draw the faults, let's say. So there's always a difference between picking them from seismic. Let's say you have a 3D seismic and you want to get this feature basically in your 3D visualization. Or if you want to consider the faults really as affecting your layer stack and you want to model the geology. It's my 5 cents. Maybe Miguel wants to add.
Yeah, yes, adding a bit to the whole thing. So in my opinion, the faults is not a different problem than the overall complexity of the geometry. So if you add complexity to the geometry that goes against the interpolator, you start having similar problems. The problem with the final faults is that suddenly you are adding an area of local anisotropy that a lot of times the data doesn't fit. So the overall problem that I think that we have to try to solve is how we scale the complexity on geometry. So, and here is really where local anisotropy using multiple drifts so that the model is not so tense. Because something that in the presentations today we didn't talk about is all the secrets and details that we have to put into the interpolator to get proper results. Because normally the system of equations is really ill-posed. I mean, I remember the first time talking to Mike Hiller that he said that in his package he was using floats 256 to be able to solve the problem, and that is not disclosed anywhere. So all these interpolators are fundamentally ill-posed because the geology is ill-posed. There are many solutions to every specific set of input data. So as we are getting better and better to deal with those type of complexities, I think that the faults will just follow.
I mean, the way
in any case, I'm sorry.
Let's go with Andrea, then Tim, you.
Yeah, cool.
Andrea?
To say that faults in many cases are a huge problem, and the way you deal with them also depends on the application. I mean, in a regional model, you focus only on the large faults that create a consistent offset that you cannot ignore at the regional scale. On the other hand, if you are dealing with some, I don't know, engineering subsurface project, like a tunnel, a huge chamber for some, I don't know, hydroelectric plant or something like that, people who are designing these objects, they are interested also in large fractures. because they have a very strong geomechanical impact. They are interested in the thickness of what they call damage zone in an engineering sense, and so on. So, I mean, the way we implement the faults in the model, the way we represent them, the way these faults are associated with other properties in the models, like fracturing around the fault and so on. This is very important, and it's different depending on the application. And so probably there is no unique solution also.
Tim?
Sometimes you end up being so much interested in faults and fractures, and maybe you are in a homogeneous geology. So interpolating the stratigraphy is not important, and you end up modeling with standard, all times explicit methods, because in this way it's easy to represent all fractures. And then maybe you are in a homogeneous gneiss and you forget about the stratigraphy. So it depends on where you are.
Just sort of following on from that, one of the things I'm increasingly doing, and okay, this is using GeoGoCAD, is starting off with the faults you can see in seismic, because we know they're there, and they often are the big structures that are defining your domains within your model. And then actually then not fitting the model to the markers, and then using that residual on your borehole data and your import data as to highlight areas where you need a fault, because quite often I'm using, this is near surface modeling, so this is mostly in coalfield areas, and we have thousands of faults on our maps, many of which are some miner saw something that displaced something by ½ a meter. Some of them will be there because they were using quite limiting and quite old structural understandings. These have been mapped in the 1920s, so they didn't know about plate tectonics. The fault networks didn't have to move kinematically. So actually using that iterative approach where you test the model, use the error as you can calculate it off the model to identify where you need a fault based on your input data, and then go back to your map data and then go, okay, those, I can see that structure definitely exists here, because I can see an offset, but over here, I think I'll redraw that. So it is using it in a little bit more of an iterative approach, but then you end up with the result that is a fault network that fits the scale of the model. And this comes back to this whole thing of scale in 3D, which is obviously kind of hard. So often when I've tried to build fault networks that have gone wrong, I've been basically trying to model faults that are either too big or often too small for the scale of the model. They're not producing a substantial offset on surfaces. So yes, there may be a fault there, but in reality, it's probably a much, it's going to be within the noise volume, the noise of the model itself.
Okay, thanks. Andrea, you have several questions directed to you about P0. So I'll leave you answer them in the chat or in the question and answer box. Florian, we wanted to add a quick comment.
No, I have a question.
Sure. Ask your question.
I have a question to the surveys.
Okay, just ask your question.
As we are here. So what is actually the vision of the surveys in terms of supporting open source tools? I mean, we can all sit here and wait until they are developed, and we see developments which are coming up, but it's really difficult to keep these afloat for anyone who is in this field, right? It's very difficult to support open source projects from university funding, let's say, because this is not what research funding is there for. So what is the vision of the surveys? Are the surveys interested in investing and becoming basically part of the development, or are they waiting until there is a good enough code to switch from GoCAD or Leapfrog, and they want to have a perfect solution which is then suddenly free? What is the vision?
Yes, I have no authority to answer for
what
all
is your
surveys.
Vision? Let's start there. And I'm asking this the entire audience here.
The easy answer is that the goal of the whole task that we have been setting up in the GSEU project is trying to answer this question and trying to develop a kind of consistent answer to your question, and also trying to explain our management, I think, how we could rely on open source developments and how we cannot, because not everything is not clear still. So a large part of the task is trying to have a good vision of what exists and trying to explain how we could and define how we could use collectively and invest. Though we are not a funding agency, don't worry, don't don't forget this. So I don't know if someone else wants to.
Yeah, well, I mean, you pay for licenses, right? So that's a bit the question. So
yeah, you're right. Miguel, you wanted to.
Yeah, no. So what I wanted to add on this is that in the last months, years, some of the geological surveys they started to ask for teaching and consulting on GEMPA, yeah? And so far we are doing it over my company, but I think that that is not the right way. So if we will have an external entity where anybody who wants to organize a workshop in something like this wants to participate, that to me is the better future. So
Yeah.
really just maybe because at this stage, I mean, a lot of the investment that some of the geological surveys are already doing, everybody benefits, but it's only one entity. So if we will be able, I mean, obviously super hard to coordinate all of these things. But,
yeah, sure.
But now it starts to be already a coordination problem of who is the first one or if everybody is the first one.
I'm not sure. I'm sorry, I'm interrupting you. I was thinking that maybe we should have had a larger discussion slot. Maybe we could just convene and have another discussion, a full discussion, a morning or afternoon. Could be interesting. It's kind of discussion. I think we all need a break. So there are many questions in the chat, and we can continue this discussion about investment or maybe governance, because I had question in return to you, Florian. What would be the governance of your foundation, for example? In an open source project, very often it's the committers with the highest experience who have the power. And in private consortium, obviously, it's the people who pays who have the power and the decision power.
Yeah.
There are many decisions. I'm sorry, we are going really to have a break to stay on schedule. Yeah. Just continue to interact in the chat.
Yeah.
And if you're interested in continuing this discussion, we can just meet again. I think it's a good idea to have this kind of discussion with people interested in the subject. I propose you to convene again in, let's say, 7 minutes. That would be 35 to 11. So we'll be only 5 minutes late. Okay, let's start with your talk. I guess you're the one talking.
Yes. Do you hear me correctly?
Yeah, perfectly. We don't see your screen yet, but maybe
Not yet.
It's coming, I guess.
But it's gonna come.
Perfect.
Is it?
Yeah.
You see it, I don't see it. Okay, I've got it. Okay, so I'm Didier Renard from the Paris School of Mines. And I'm not gonna follow exactly the same topic as the previous speakers, as I'm not doing any advertisement of a package. In fact, if I wanted, I would defend a library that we are establishing. So it's a library that you can use it. And I will give a small information about this library at the end of the talk. Okay, and I'm concerned about the title, which are methods of interpolation and simulation. And I added seen from geostatistical point of view. And I'm going to try to cover a little bit of what I've been doing to address that topic in terms of geostatistics in my memory in the past of several years. Okay, don't be frightened by the number of slides, as Simon was in a minute, because I have shortcuts. I just prepare things in case you have many questions. Okay, so I converted the title Geomodelling in saying that essentially what I want to do is to create envelopes or to try to speak of domains. Okay, and the talk is going to be illustrated in 3D essentially. And thinking to myself, what do I have to do domaining starting with? I imagined that essentially I had to work either with data coming in 3D, generally along well. They can be given in grade or directly in geology, or I can have markers, as we mentioned in several talks earlier, for implicit models, for example. And so I can have markers and I can look at my data in 3D, but concentrate on markers only. And the second thing, and this is where geostatistics comes from, we know that we can provide the best case, usually known as a kriging solution, kriging co-kriging, or through simulations. And this is what I'm going to cover next. So I will always concentrate on this very simple 3D schematic example. So you've got wells, and most of the time you measure something that I will call grade. And this grade here varies gradually, and it calls for a three-dimensional approach where the grade is going to be given with 3 coordinates and possibly present a vertical trend or not. Okay, and the idea is to find the envelope. So possibly if grade is filled all over the area, we are simply focusing on places where the grade lies within an interval. Okay, and that for me calls for some methods, and one of the methods that I can imagine for that, for tackling these problems, is the pluri-Gaussian. You've got some references sitting here. Okay, so what is the idea of a pluri-Gaussian? What is beneath the cards? You've got data, and the first thing you want to do is to simulate underlying Gaussian random function. Okay, so everything is based on an underlying Gaussian random function. So the first step is to convert your facius information into Gaussian. That refers to gift sampler algorithm. Then you run your conditional simulation in the Gaussian framework, and then you code your Gaussian result back into facius. So this methodology requires several types of parameters, such as the way to convert facius to Gaussian and vice versa, and of course the special characteristic of the underlying Gaussian function that you want to simulate. So if I want to sketch a workflow, I will say that I take my data. I usually have better to flatten them in the structural system, in the system where the correlation, the maximum correlation becomes horizontal. I call it the working system. Then I have to translate grade into facius. Then I have to infer to set the parameters if I want to have proper results. And the parameters that I sketch here are the proportions. How many of each facius do you have to simulate? The truncation scheme, which governs the architecture and the proximity between different facius. And of course, the special characteristic of the underlying Gaussian random function characterized by a variogram and a corresponding model. And when this is done, you simply have to run the conditional simulation and back transform to a structural position at the end of the game. Okay, so I illustrate that through a simple case. So here I gave to myself 160 samples measured along wells with different proportions, 4 facius. And this is the truncation rule, which gives me the proximity of the facius, yellow sitting close to, and so on and so forth. Then I have also the structural of my underlying random functions. Here I need 2 of them to characterize my pluri-Gaussian. So here you've got your sketch of your set of data, which are color coded by facius. And what you want to do is to populate that with pluri-Gaussian simulations. So these are 3 output of conditional simulations that we ran on the previous data set with the previously defined parameters. Okay, and then what you can do if you're looking for an envelope of something is to concentrate on one facius. For example, concentrating on the facius number 4, the yellow one of the previous picture, and looking at one simulation in particular, then you can extrude this facius and call that the body of your target body. Okay, what we see here is that things are nicely organized. They cover the conditions. They have the correct extension in terms of what is described by the model. But sometimes people can say that you do not control the connexity or convexity of the field facius or of the envelope. Okay, so I imagine another model that we have been using in the past which is called the Boolean model. And again, some quick references here. And the Boolean model has different ingredient than the previous one. Basically, it's based on a random set denoted X, which is controlled by a set of objects simulated independently one from the other one according to a law that I call A of X. And basically the X, the location of the objects, is governed by a Poisson-Point process, which is ruled by its intensity. If we want to give a little bit of scenario, we are able to run this Boolean model conditionally to the data. The idea is to simulate a first run of primary object, having the task to cover the conditioning points, that is to cover the grains and not to cover the pores. We are discussing over two colors, grain versus pores, facies versus outside of facies, if you will. And finally, you have to destroy your primary grain and replace them by secondary grain or objects, which will cover the conditions and be randomly located, covering the field according to your Poisson process that you're targeting. Okay, again in gradient workflow, so you have to translate your grade into facies. Now again, facies is going to be the thing that you're looking for, and the rest is going to be called background. It's going to be a black and white image, if you will. Then you have to define the library object of type of objects that you want to simulate. Okay, and give the characteristic of the Poisson-Point process and define its intensity, a proportion of objects, and then run the conditional simulation. So again, on my quick example, these are my well data, as you've seen before. Then I designated the facies of interest, represented by yellow points, difficult to see. I have very few yellow points, 11 out of 160. Then I gave to myself a proportion of objects that I want to simulate. This is usually derived from the data set. And this is the simulation of it's one of my simulation. And again, I extruded the facies of interest. So this time you see clearly the envelope, which consists of a series of objects. The object type that have been selected here is ellipsoid. Okay, so here we have tackled things through 3D information. Now there may be another solution. If we look at my data again along boreholes, and maybe the grade is going to present some sharp transition this time. And that calls for getting the markers. Markers is the location where the sharp transition appears. And of course, what we want to do is do an interpolation of the surface. And clearly the surface now is coming down to a 2D approach. My surface M has coordinate X and Y. Yeah? Okay, side problems that we have is, what happens if you have this type of things? Clearly, we have two types of sharp transitions, okay, that we can regroup by types. And we are looking for sets of 2D surfaces. Okay, well, obviously we have to tackle this problem considering the different surfaces simultaneously. Okay, now some other pitfalls or problems is if you have this, clearly the top layer goes down regularly, so that calls for something non-stationary. Whereas the second one, M2, nicely follows M1. So question is, should we work with M1, M2 as depths, or should we work with M1? M2 would be considered a thickness. M1 would be non-stationary, the thickness could be considered as stationary. Okay, another pitfall is what happens there. Of course, clearly we would like to avoid having M2 passing above M1. Okay, the inequality that I heard we discussed this morning, Andrea, if I'm correct. Okay, So these are pitfalls that we have to avoid. And last but not least is what happens when the wells are deviated. Clearly, we have to replace depths by TVD, true vertical depths. Okay, and for the first layer, true vertical depth is not an issue. For the second one, clearly things are more difficult because if we look at what happens per well, we have the TVD gives us the sum of the thicknesses, but does not provide any value for each thickness in particular. So that has been developed into another project, which was entitled Multi-Layer Methodology. So multi-layer methodology covers the following ingredients. Basically, we start from a reference surface, which is supposed to be known everywhere. Then we manipulate, we tackle with a set of wells. They can be vertical, inclined, deviated, at least in the oil and gas project where we use that methodology. We've got markers of seismic horizon, which means that on the side, we also have seismic time maps, and we have to match everything together. So the methodology in my slideshow, I prepared something, if we had time, about sequential approach, which seems to be not very promising. It replaced by a direct approach where we tackle all the thicknesses simultaneously through the TVD, as we've seen a moment ago. And this has been addressed in the North Sea, a North Sea field, working with Statoil at that time. And this is the cross-section, vertical cross-section of different time maps with the deviated wells reproduced on the time section. Okay, and these are, that gives you a flavor. These are the time maps seen from above that we had for each of the horizon. Only 2 of them have been displayed here. Okay, and after running the multi-layer process, the time section picture, you have it on the left, and the resulting cross-section expressed in depth is provided on the right part. And you can see, if you could zoom, you could see that wells have the information at wells has been fulfilled correctly. Yeah? And now if you want to see the result, you've got, again, the type map of the marker called B1 on the left, and on the right side, you've got the depth map of the same marker, which has been chopped on the right by a truncation, which you see on the top of my structure here, which is an erosion by an erosional surface. Huh? Okay, and here you can see that I changed my language. I'm looking at the creek solution, but the same technique can be also run into simulation techniques. So you've got for the same case, basically, you've got the kriging version on the left, excuse me, and one conditional simulation on the right. And of course, you've got all the benefit of being able to run several simulations, if you will. Okay, now, of course, what I did not address is this type of thing. And here I'm looking for a folded surface. Okay, and clearly the layer cake framework has to be abandoned. Another point is this type of feature where I'm looking for envelopes or nested envelopes even more. And of course here I'm looking at the potential method, which is or answer, just statistical answer to the implicit methodology. So the implicit model has been addressed several times by a previous lecturer this morning. Okay, so we are looking at an underlying random variable that I call potential, which is controlled by the data, and the data are looked at by increment. Okay, simply saying that 2 points belonging to the same interface have the same potential value, so they belong to the same isoline or isosurface, if you will. Okay, so this is governed by the set of markers, some gradient information giving us the orientation, and possibly tangent information are passed. And you can run estimation, a little bit more difficultly simulations, and that can be run in any space, no limitation. And again, an illustration. So I've got my wells here. Okay, here now I have been reducing my information drastically to the only markers, as you can see. Okay, markers which are the intercept of my well with my envelope of interest. And here I'm looking, just for the sake of simplicity of this talk, to only one mineralization envelope. So my envelope has to go through all these points. And so I'm carrying the implicit simulation, which gives me the value of my potential underneath field. Roughly speaking, it varies between -4 and +3. Remember, these units have no real meaning, yeah? And what I can do is inquire the value of this potential at the markers. And here the value that I'm looking for is the value of 0. And here I'm displaying the potential, but not the potential filling the whole space. I'm concentrating on isosurface. And you've got the potential value on the top there. And you can see when I read the value of 0, sorry, it goes in a loop, it's not very clever. When it reaches the value of 0, that is the one which goes, that is the surface which goes through any of the intercepts, okay? Okay, and as a conclusion of my talk, just to be on time, basically my point of view was to look at the dimensionality of my space. Okay, here I use 3D. Then the dimensionality of my information could be 3D, okay, and or could be reduced to 2D with an additional hypothesis of a layer cake simplification, where you have more specific answer. And another point is to look at the 3D, but partially, like only focusing on the markers, and that calls for implicit modeling, for example. Huh? Okay, all the different techniques that I explained a moment ago. Ready to answer your question if you want to know more about the techniques, each one of them. And everything is available in the library, GSTLearn. So this is my advertisement last slide. So this is an open source library. It's available on GitHub. It's a C++ library which can be accessed through script written in Python or in R. It's available for different platforms, as you can see. It's multidimensional, multivariate. It tackles many, many different things, and it's the place where our center is developing our new tentative of methodology. For example, I named space-time models that we are developing. Okay, and this is it for my presentation. Thank you for your attention. Thank you.
Thank you, Didier. Thanks a lot. So it's very interesting to have all of these modeling algorithm grouped in a single package, reflecting a long history of development. And we have one question from Tom, who is asking, for the wide range of interpolation methods available, what guidelines would you use to determine which method is the most suitable? I guess the
answer is just look at your data. Look clearly as you add hypotheses, you're tuning the type of result that you're looking for. Okay, and specifically the multi-layer, which was really appreciated by Statoil at the time I developed that for them. That was really specific for North Sea multi-layer, quite regular type of behavior. Okay, I should add that nevertheless there were a lot of faults there. I agreed with the talks regarding faults this morning. Okay, we are not very good in faulting right now. Okay, it's not our cup of tea really. I would, if I refer to the comments of Simon this morning, he said either we are discussing fault or we are discussing uncertainty. Clearly, we are on the side of uncertainties. All the method that I explained, they have their, either you can do kriging and therefore you have your variance of estimation, blah, 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 or you have simulations and then door is open for doing any uncertainty analysis. Okay, faulting for us is something which comes on top, which does not make life easy. Yeah? I agree, yeah? But it's not our cup of tea. Yeah? And which method should you use? It really depends on the hypothesis you are ready to put on your on your game. Huh? Okay.
Okay, thank you. We're running a bit late, so I'm going to introduce myself as I'm the next speaker and share my screen, and we'll have a small discussion slot at the end of after the presentation by Tim. So thank you again, Didier. I'm going to give this talk about what we are currently doing at BRGM. So it's really a teamwork where several of us are working on this. And we're trying to refactor our all good geological modeling algorithm and tools into a single platform. And currently the target is QGIS, but there are also several targets. It's more or less a talk that we've been giving with Nicolas 2 years ago at the IMG, then we gave it again at the Ring meeting. Each time there are a few updates. And I kept the subtitles, which I like because it's really like trying to make a balance between keeping all that we have, some codes that has been developed for 50 years, really, and starting something new, like it could be done, for example, with GenPy or Loop. A few years ago, they started nearly from scratch, just looking at the paper and recording everything. So this is more or less the context of my talk. I don't manage to switch slide. Yes, there it is. Just small configuration, trying to switch from speaker to sorry, yeah, here we are. So I'll very few words about the context, and then I'll present the work. I try a demo. I'm sure, according to Murphy's law, it should fail, but we'll see. So what about the context? I'll go very quickly on this one. It's first thing, and maybe it's a part of the answer to Florian, the survey's activity really vary from one country to another. The size vary too, and the thematic they are involved in really vary. Maybe a common mission is at least to provide reference data and expertise about our national subsurface. And to do this, structural modeling is really a cornerstone. That means for a long time, we've been focusing on surfaces and boundaries, what we call structural modeling. We are progressively moving towards properties. Some surveys are much more advanced than others in trying to characterize properties, physical properties of the subsurface, but structural modeling has been here for a long time. And at BRGM, we've been developing two main solutions. So we've been using a lot of software, commercial software. And when this software were not enough, we've been developing our own solutions. Between the several solutions that we've been developing during 50 years, two of them worth mentioning. I guess it's a GDM tool, which is a relatively simple tool where you pile up layers. So it's a multi-layer approach, as was presented by Didier. And the Geomodeller tool, which was one of the first tools in the late 90s to implement an implicit approach to geological modeling. These two tools share common DNA. They're really, I think the most important one is that they've been developed for operational purposes, though what we need, it was also an answer in the chat, we need operational tool really. I think it was the most important point. And Geomodeller, at least, has really been developed with field mapping in mind. It was at a time where the GoCut consortium was really focusing on the petroleum targets, oil and gas targets, so sedimentary basins, relatively simple in terms of structures. And it was developed trying to integrate all what we needed to do numerical field mapping. And I would also add another chromosome, to this DNA is geostatistics. Both tools are really developed in the geostatistical framework, and both tools have been developed in collaboration with Mines Paris. GDM 50 years ago and Geomodelling 25 to 30 years ago. I think I will go very briefly on the tool. So as I said, GDM multi-layer approach. So it's what we call 2.5D modeling. You are stacking stratigraphical layers, and it's an explicit modeling from the point of view of the mathematical function. That is, you are stacking elevation maps, and you are interpolating either elevations or thickness to build these elevation maps that you are stacking. GDM was standing for Géologie des données minières at the time when it was developed. It was French, and we've been reshaping this to geological data management just to insist on the fact there is also all the geostatical toolbox in GDM to work on your data, do cross-validation, quality checking, and this kind of things. So I'm not really selling the tool because it's no longer sold, not really sold, but really trying to explain why we need them. And so, as I said, Geomodeller was originally developed for field mapping, so 3D, the transition from 2D maps to 3D geological cartography. And to do so, we had to take into account complex geological architectures, so relations between layers like erosions, but also faults and fault networks or intrusions. And at the time, Cochrane revealed to be a very interesting solution to solve at least a vast part of all of these problems. As we've said, there are still many open questions. But it was the first time that we were able to integrate location and orientation data to characterize layers, geological layers. And that was really a difference because at the time we were just dropping all orientation data, and orientation data was one of the most important data that geologists were collecting on the field. And maybe there is the next step is probably integrating uncertainty constraints, and the presentation from Lachlan on this point was really interesting. Geomodeller is also used by geophysicists because it has some geophysical forward and inverse modeling integrated. And there have been some developments at the time about unstructured mesh generation for simulation applications. So starting with these two historical tools, what is the current BRGM roadmap at the institution scale? It's not really original. The current target is trying to be able to combine everything in a single approach, or at least in a common ecosystem. And we're trying to implement the transition from desktop tools to information systems. We're still in the middle of it, let's be honest. So the idea would be to easily explore existing models, relying most of the time on open modular components. That's an important point. But in trying to take the best from each approach, combining these modules to build models, and ideally integrating information building information models, on LiDAR with geological models. There are a lot of expectations put on AI and automation. I won't talk about this. Quite interesting, a lot of things to say, but I won't talk about this. In this framework, a lot of people at BRGM focus on workflows tool. How am I going to be able to combine everything into the survey's activity, considering that geomodeling is only a small part of what people do, at least at BRGM. We have very few people who actually do geological modeling. They are experts and they want an operational tool to be used. But the curious point is geological models are everywhere behind the surface of all activities, because if you need a quantitative approach of the subsurface, you need a 3D model. To do this combination of workflows, we are currently exploring the Galaxy framework, which is also an open source tool, but really dedicated at workflow things, and to implement workflow tasks. when you talk to people involved in describing workflows, it often ends up in something like this, trying to isolate every task that you want to perform with different steps. This cartoon was drawn in the framework of the GSEU project, trying to identify what were the different steps of geological modeling. So obviously there are a lot of things concerning the data, interpretation of data, because very often geological modeling step is when you refine the interpretation of the data. So taking into account interpretation is paramount, and you want to be able to come back to this interpretation, test hypotheses, and so on. And on the right, you have all what is the I would say the kind of engine that Florian has shown with the motor thing, this big engine, and you want something that works and show you the nice surfaces. So we have identified more or less 5 steps, and the workshops in GSEU are organized around these 5 steps. A last point, but not least, at least in France, there has been a law, and everything concerning the data, and this includes code that we produce using public funds should be open and available to everybody. So this has already been a big switch in what we are doing. So which bricks are we going to use? I won't talk about the previous bricks because we had very interesting talk about all the open source initiatives in geological modeling that already exist and that we can use. I think maybe they are not operational too, but they are robust enough as of today, I guess. And for each domain, there are many libraries. I think that the 4 examples of this morning are only a few of them. What's interesting is that when you go into surveys and ask people who are doing geological modeling and ask them about this initiative, its result is this kind of graphics. So we were in a framework of the GSEU project. We make a form, sent it to the survey to people doing geological modeling, and ask them several questions. And one of them was, do you use open source framework to do geological modeling, or were you able to mention one? It's not a contest, so you're not going to say who won and not. I think the one who won is the ignorance. So people were not aware really of what they could do, and they were not using it. This was presented in Busan last year at the International Geological Congress. So we need a place to integrate all of this package, and at PHM, it seemed to us that QGIS was an interesting solution. So why QGIS? QGIS is an open source geological information system. At least at BRGM, but I think it's the same in a lot of institutions. A lot of people are using QGIS on a daily basis, much more than geological modeling software. It's free, it's open source. It's becoming more and more a powerful toolbox to handle georeference data. A very interesting aspect, it allows seamless and easy connection to data sources and web services, and it's really an integration platform when you can gather a lot of data. Still, most of the time 2D data, but more and more 3D data. It's widely used. There is really an existing community with an ecosystem of solutions. For example, QField, to use QGIS in the field, that people are using it more and more at BRGM to go in the field. It has extension capacities through plugins, easily written in Python. For example, on the right, is something that we had done 3 years ago, just plug in the Geomodeller algorithm into QGIS and showing a model, exploring a model in forms of map or cross-section inside QGIS. It's evolving. It's evolving very quickly on the 3D aspects. It's integrating more and more 3D capacities. The viewer is still lagging. It's not really good. Cross-section also, but it's evolving. And there are more and more plugins targeting geological applications. For example, I could there is OpenLog for borehole management. Yet, this was the pros. These were the pros. On accounts, it's really not fully 3D yet. There are no real unstructured data. So more or less, it's at the time being, things are really moving very quickly, and in next release we should have instructor meshes. But at the time being, it's really what GM does. So you can pile already elevation maps. And make QGIS Advanced would imply core contributions, and it's what we've been trying to do. First, developing plugins, and we really realized that managing plugins, external dependencies could be hard, really a nightmare. And when I say nightmare, I really mean it. So there are several technological solutions. I won't go into this. I won't go into details. The main point is that it is evolving, but slowly. It's evolving at the pace of a big open source project. So sometimes you would like it to evolve quicker. But at Geological Surveys, we have the habits of geological times, so it's okay. I will then just give two quick examples of what we're trying to do inside QGIS. What we want is to bring a kind of ISO functionality with our old tools inside QGIS. So a first solution was to plug algorithms from the GSEU libraries that Didier has been presenting previously. So we had made a plugin that you can use to explore your data, made a bit of variography, simple variography, and then use interpolation algorithm to make a map, an elevation map of something. For example, here taking into account faults. Okay, so this is more. So this plugin is dedicated to be kind of a geostatistical toolbox. And the other one is about structural modeling, so trying to replace all what is building a geological modeling model. Sorry. So it is being able to build a model, not only load a model inside QGIS. So as Thomas has shown yesterday afternoon, we already have a plugin to export model in 3D viewers. So I won't come back on this. And what we are targeting is really a kind of tight integration into QGIS. We try to avoid having a tool running outside QGIS and with the problem of synchronizing both. So this means, from our analysis, this means supporting the development of core QGIS functionalities. And that's what we are currently doing. For example, we are supporting development to improve what they call the elevation profiles, what we would call cross-sections in geological tools. And that is evolving quickly. And probably we could start kind of collaborative work or discussion on what lacks to make it a full 3D tool. And there is also a lot of work, as I mentioned, so how could we solve this problem of plugin dependencies that can be quite important. So I promised a demo, so I'll try the demo. This is the point where it should fail. I'm going to show just a simple vision of what we are targeting. So this is QGIS. For those who know it, yesterday Thomas has shown that we can you can load a geological model. Just to show it again. Yes, the same thing. Sorry, not this. Let's go test. Then let's load this one. So this is a Geomodelling model. I have to define a. Sorry, I have to define a CRS because Geomodelling does not handle this. And I have the framework. I could add layers with the maps and so on. And I can draw cross-section in this model. And I can extract interfaces from this model, for example, up just using processing. So this is extraction. Let's say, obviously, all of these little widgets could be improved to be more user-friendly. That's okay. And if I open the Pages window, which is somewhere else, it sent me the 3D model. And as Thomas shown us yesterday, you can, so you have the folds, you can select them, change them. You can send many information from the 2D tree to the 3D viewer. But what we want to do is to be able to build really a 3D model. So what we are developing is a kind of the small widget that you need to define your layer and arrange the relation between your layers. So basically what you have in GDM or Geomodeller. So you can start with creating a pile, defining unit. Obviously, you can change the name, the color. I won't do this because it's just demo. Let's make it blue. You add erosion surfaces. You can move the erosion surfaces. When you are happy with your pile, you create a model with the pile. Let's just name it model 2. It opens a box, and then you are going to look data in your QGIS. So you are going to scroll and your data that you have inside QGIS, select data using QGIS filters to populate the data that you are going to use to build your interfaces. You can select relation between these interfaces, and this will affect the kind of interpolator that you are going to use. For example, saying that the contact here is the top. This is the first. So first bug. That doesn't matter. I tried. Yeah. Yes, I'm going to save and reopen. Hope it will work. No, so first bug. It's kind of thing in development. It's a pity because the other thing is you can define fault network. The same way you are going to define fault relations between faults, if they stop on this kind of thing that you have in Geomodeller, and then you can select a fault network that you want to add to your model, and now you're going to say if your level is affected by fault and so on. Okay, I will just open a simple model that's been designed with the data that I have I was showing before. Okay, so I have this kind of topography with data. I have made this model. Okay, so here it says that some layers have got really information, be it contact points or orientation data. And let's see, I'm trying something, and now it's what I've tried this morning was working. Anyway, let's see if it works. This has been configured. What happens here is that when you choose a different relation, it breaks the interpolator windows on the right, and you can select different interpolator. And the idea here is that you can select different interpolation methods. For example, this model is built with the potential method, but you could use elevation maps, interpolation, kriging, and so on to build this. And here you've got a real model behind it, so you can use the same filters as we've been using with the geomodeling algorithm to extract it and send it to the 3D viewer, for example. I will make it simple. Hope it won't crash. Maybe it's going to crash. No, it's okay. Works. And if I'm going to my 3D windows, I've got here the model, a very simple model with an erosion surface, and it's not really. But the most interesting point is not maybe this 3D window, but the fact that you can draw your model on your topography For example, and you can also make cross sections. For example, last minute, I guess, of my demo, if I add a sections layer, let's say I've got cross section, I want to align. I'm selecting. So obviously, the good thing is that QGIS is going to manage all what is coordinate reference systems and all this. You don't care. What you want to do is to make a cross section. So you make your cross section. For example, here you add it, and you want to draw your model on a vertical cross section. Vertical section. You select your model. Yep. The section layer is okay. This one is okay. Let's run it. And it's been extracting the formation. So you see here on the cross section, but to see it, you must open the elevation profile window. And you're going to say, I want to see my model on this section. And here you see your geological horizon, and you can work on it, just seeing that it goes through your points and so on. So it's still in development. So I'm going to come back on my talk and try to conclude. And we really aim at a tight integration with QGIS, as we've identified it as one of the main tools of geological experts. And we think that implementing simple geomodeling capacities, we're not targeting replacing a commercial complete suite of software. Really, simple geomodeling capacity in GIS systems should bring more people to geological modeling. For example, all of the hydrogeology people in Belgium, they worked with QGIS, and we could bring them to producing geological models with this kind of tool. The other point that we realized, that's the fact that our users were working with mature tools was partly shaping the way they were expressing their needs. And we really have a lot of work in terms of cultural change to bring them from GeoModeler and or GDM to QGIS. And that's an also very important point, how you bring users to your tool. And last, all what we are doing should be released, as you say, it's by law now, on our public GitLab slowly. Sorry, it's really slowly but progressively at this address. And I'm running a bit late, so sorry for this. That's it. Yeah, demo effect. Demo effect, definitely. Yes, I think as I've been talking too much, it's the fact of being a speaker. Maybe Tim, you can share your screen and
yeah, okay, I'll get going. Okay.
It was about choosing the good one, is it?
Well, this is going to be a slightly different talk from the ones previously, which is rather than focusing on methodologies, it's actually trying to compare them, because there's one of the questions that come up in the chat, and it's one that I often get asked is which, if you're new to 3D modeling, there's a wealth of opportunities and methods out there. What works, what's best, what should I use? And this was an opportunity. It's actually it's been going for quite a few years now, kind of got stopped by COVID, and we've now started back up again, where we've actually had to try and look at this question in the real world. So, sorry, I think, there we go. Okay, so what I'm going to be talking about today is a national model that we produce in the BGS, the British Geological Survey. So apologies, I haven't introduced myself. My name's Tim Kearsey. I work at the British Geological Survey. I've been here about 20 years now-ish. So one of the things we produce is the thing called the National Superficial Thickness Model. Now, this is a very old model. It was first developed in 2001. And it was created by I think, if I remember rightly, in Map Info, the original version was. It was created using 450,000 boreholes, proving the top of bedrock. So this is basically a top of bedrock model. And then they also used the extent of mapped quaternary or superficial deposits. It was interpolated using well, at the time, quite a sophisticated interpolation method, but I think things have moved on quite significantly. So they use a natural neighbor interpolation with a weighted Villani point neighborhood around each point. So it is quite an old model, but actually it's one of our key models. So why is this an important model to do? So this really quite hideous flow diagram here actually shows how we use some of our sort of baseline data sets to create derived data sets. So this is our sort of geological mapping, and we use those to create data sets that are relevant to the civils industry, so the geotechnical industry, coast vulnerability, pipeline impact, insurance, groundwater stability. So and the superficial thickness model is sitting down here at the bottom, you see here. So it is a key data set that we absolutely rely on to end up in quite a lot of derived products, which are actually used by quite a large amount of the UK to make proper decisions on. So this isn't some sort of theoretical thing. This is a data set that actually people are making decisions on a daily basis. So let's have a look at the input data. So the only subsurface data we use in this model is borehole data. And this is mostly provided by third parties. So this will be, the vast majority will be geotechnical boreholes, so boreholes drilled for ground investigation. We have some former mining legacy, particularly boreholes, particularly in our coalfield areas. We have water wells. We have some deep boreholes, mostly drilled for hydrocarbon exploration onshore. So that's the data set, and it's a data set that we obviously didn't create as a geological survey, although we did. There are probably several hundred boreholes that we did drill as part of our mapping projects, but the vast majority is by other people. It is a highly clustered data set, and I think this is one of the things that is always a challenge, regardless of how we're modeling. And one of the differences between the sort of slightly more theoretical world of developing these softwares and the real world of trying to use them, where we are always using highly clustered data sets, and this actually creates a whole set of issues in its own right. However, you can turn that on its head in the fact that we have a map of where stakeholders across the UK are interested in the subsurface. The borehole map tells you that because it's mostly derived from third-party data, and as you can see, it's the areas of population, and then the major trunk roads, which are the ground investigations that went along those roads. So when we started, so I got involved in the SDTM project again about probably 5 years ago, and one of the first things we started to look at, we realized that there were some issues with that old interpolation. So there are apparent gaps. So this is a feature up here as a tunnel valley, and we'll talk about this a little bit more in a moment, where we had sort of apparent gaps. There were areas where we had blobbing, and there was a serious problem in the upland areas as well. It was predicting quite significant thicknesses on top of mountains where we know there's rock. So one of the things that when I first got involved in this was to try and look at the role the different interpolations were making on that impact, because obviously we're relying on the interpolation to make sense of what's going on away from our control data. And I think it is worth just taking a back step here, because if you think about it, unlike geological mapping, where pretty much every boundary is hand-drawn or can be hand-drawn, obviously increasingly we can use remote sensing, but you as a geologist have a sort of hard control on where that boundary lies. All 3D modeling, regardless of how complex it is, relies on interpolation to be able to extrapolate between points. So unlike mapping, you are always reliant on some element of mathematical calculation to produce that model. And as we've seen today, this has been increasingly sophisticated over the last 25 years, and I think we'll see later today that actually this rate of change is not tailing off. This is still going up, and I think AI is giving it another kick upwards. So the methods available to us of increasing and evolving probably on a yearly, definitely on a decadely basis. So I wanted to sort of do a very simple test and say, okay, I'll test three algorithms. So I tested the direct triangulation, which is probably the simplest thing you can do. So dot to dot between the points. I tested the natural neighbor interpolation, which was the previous method that had been used to calculate this surface. And then I tested an implicit modeling algorithm. So this was the implicit. So this is the skewer. I used the skewer variant of the implicit modeling. And of course, as we've seen for the presentations earlier today, these things work in quite different ways, and they give you supposedly more geologically realistic results. So the test area we worked on is, again, this buried valley. So it's a tunnel valley. It's a glacial tunnel valley. It's near Stirling. This is it. So the town of Stirling is on the low ground there. There's high ground above it with which is actually volcanic deposits, and then there is this buried trough feature the deepest borehole has proved to be about 90 meters deep, so it's quite a significant feature. This is the input data. So this is the borehole data here, colored up with depth. So you can see so red is deep, blue is shallow. So we can see we've got quite a variability of rock head in this area, the variability of the topography on the top of bedrock. So we thought this would be a really good test to just sort of try these out. So again, I used the same input data that we use to build the national model. So I used the terrain model, the borehole intersections, and the mapped extent of superficial deposits. And I ran it through a direct triangulation, nearest neighbor interpolation, and a skewer implicit grid. And these are the results. So that's what you get if you run that data through a through a standard triangulation. This is what the nearest neighbor calculated, which is quite similar to the national one, which is good. I could replicate the national one, which is always a useful opportunity to just test that you can replicate methods. And then this is what the implicit modeling showed. So you can see that even these three models all have exactly the same input data in them, but you get quite significantly different results, particularly around these buried valley features. So obviously what I wanted to do is go and test this, because we have three different answers. I wanted to know what the answer was. At this point, we just bought in the office up in Edinburgh. We just bought one of these little passive seismometers. These things called Triminos. Allows you to run really quick shallow seismic, passive seismic surveys without having to put long streamer arrays and return phones and using active sources, which is a little bit of a pain because you have to get permissions for a lot of that. So we went to this feature. So this is was sitting on the buried valley feature here, and we shot a set of lines, and this is kind of the response you get back. In this kind of geology, it gives you the first good return below the surface, which is rock head. So we shot two lines, one over a very well constrained part of the system, and we made the line actually go across known borehole points, so we actually had something to depth convert with. And then we also then did another line in an area where there wasn't any control data. So this is the Trimino trace, interpolated trace from the area of the well constrained. But you can see we've only got boreholes on the northern limb of this feature. We then had another trace on the southern limb, on the area, sorry, where there wasn't any data. And again, we got this Trimino trace. And then we can now compare this back to our input line, so our three models, and say which one does the best. So, so if we this is the responses for the constrained survey. So firstly, in those areas where we have the data, all models behave the same. We kind of knew that, but it's always useful to prove that. In those areas where the feature was less constrained, the direct triangulation, not unsurprisingly, because it is a dot to dot, gave us the worst answer. The natural neighbor model was not that dissimilar, actually, interestingly. And then the skewer, which is the implicit modeling, actually performed slightly better, but not that much better. In those areas where there was no data, both the direct triangulation and the natural neighbor models actually provide, as expected, didn't give much answer. The natural neighbor, sorry. So yeah, the direct triangulation and the nearest neighbor underestimated the depth to the base of to Rockhead by about 50 to 60 meters. Interestingly, the implicit method over predicted it by 16 meters. So no one gives a perfect answer, but it does show that particularly in areas where you don't have data, your choice of algorithm is really, really important. So looking forward, so that was work that we did. Unfortunately, it was just before COVID. A lot of it got put on pause because of the pandemic, but we've now picked it up in recent years, and I was just sort of because where we've gone. So trying to unpick what we found, we realized that so implicit algorithms are really good at creating smooth surfaces. So they work really well for U-shaped features, this was a U-shaped feature. It was a test bed, so it did work quite well. However, they do probably introduce a degree of artificial smoothing. So if you expect your surface to have steps in it, there could be buried terracing, there could be fault scarps of unmapped faults. There you are going to over smooth that surface. So again, really what you have to think about is what algorithms you're using and how to what algorithm you use has quite a significant effect on the output surface, particularly in those areas where you don't have data. And final point, again, this is something I tend to bang on a lot about, which is the absolute fantastic advantage of validating your model against new data. As Simon highlighted, geological surveys have been working on 3D modeling, well, BRGMs for 50 years, BGS are probably slightly less than that, but still at least 30 years. We now have models that we can validate and test things against. And that is a really, really powerful thing to actually try to understand the accuracy of what you're trying to create. So where are we going next? So, and this is, I think, hopefully a good segue into the talks that are going to come after lunch, which is we are now looking at using machine learning. So so we know that even the implicit algorithms don't perform particularly well in these low data areas. So we're going to have to do something different in these low data areas. Also, implicit algorithms are quite prone to overfitting quite significantly. So I don't know if you know what overfitting is, which overfitting is where if you try and tie it to data in those areas where you don't have data, you end up with spikes. You end up basically trying to fit, it's a sort of signal to noise ratio. And often implicit models, I found, if you try and tightly fit them to your observed data, and there are large gaps, you end up with these spikes in areas where you don't have data. And these are basically a result of overfitting the data to the surfaces. They are quite common. They're slightly more complicated than I've highlighted there, but there's a LinkedIn article that I wrote a few years ago on this. But it is quite a problem. And again, it's something that we're starting to realize is not just true of implicit models. You can get it in older GoCAD models as well. But you do have to start thinking about the sort of signal to noise ratio of your surfaces and whether you should fit your data directly to your boreholes. So where are we going next? So what we're actually looking at is trying to use machine learning using terrain derivatives to provide an estimate in low data errors. So this is a bench test. I was hoping to give a full talk on this, but unfortunately various things went wrong. And we've only just got this working literally about 2 weeks ago now, or maybe even, yeah, 2 weeks ago. But what we're probably going to do is trying to use a machine learning method to create, using terrain derivatives and the borehole data to create a sort of best fit across the whole country, and then we might then refine that using maybe just in simple kriging in those areas where we have the data to make the model fit the data. But it's moving away from this data in, build model, and then create an output, to actually we'll use multiple methods to build what will probably be an amalgamation of several different methods, but because there's no one method that we can use that will help us develop something of this scale or with this degree of clustering. So that's all I wanted to talk about. Hopefully it's subtly different from what everyone else has been talking about, but I think hopefully it's given a bit of context and a food for thought for some of the discussions.
No, perfect. Thank you, Tim. Perfect. It's very good introduction to this afternoon, as you said, and it's always good to see some real data. I don't know if there are any questions in the chat or question and answer. Nicolas. It's a bit hard to animate the session being one of the speakers. We had given this name about hybrid geological models and to the discussion, and the idea of the 3 talks was trying to link the things together. For example, Didier has presented GSEU, which packages a lot of algorithms, some new. He has not shown all the algorithms, but some things are very new in GSEU, and other are very robust, proven algorithm and methods. So you have all of them. You don't know when you have too many algorithms, you don't know which is the one that you have to select. So clearly the answer, but look at your data, think about your data. What do you want to represent? Then this was this talk I've been giving, trying to explain that we have a lot of people who are still high level. They want a GUI. They want a graphical user interface. Some of them don't want to script. Even if it's changing slowly. So we must be able to combine a different method in the tool that we are proposing to our users. And finally, we have this example of combining, but Tim, you use different tools, I guess. The SQR and what was the tool behind the direct triangulation?
Actually, I did it in GoCap, but it was using the direct triangulation interpolation. It was just the sort of standard one. I mean, wow. It is the sort of the lowest common denominator.
Yeah, but it made me think about a plugin which exists in QGIS to do geological modeling. It's called Albion. It's based on this kind of triangulation, and you just stack them. Don't know if questions. No, if we don't have questions, and no, if it's very specific questions, I think we can keep we'll try to answer them directly in the chat or later. I don't know, Didier or Tim, if you have any comment or.
I think maybe one of the things to sort of highlight, which comes back to the point that Florian made at the last session, which was geological surveys implementing. How can we implement these sort of open source solutions and become partners in the coding? I think the challenge we have, well, I have particularly in geological survey in BGS, is there is a view that open source is not sustainable. Now that is changing because we have actually been using we're developing a lot of our new mapping systems on QGIS. But so there is a sort of question there that, from sort of senior management about, is this sustainable? I think they kind of get slightly annoyed at how often things keep changing. Software keeps changing. But also, we also have the situation of backward compatibility. We do often, we have legacy models and we still want to access them, we still want to build them. So we almost have to maintain a fleet of modeling software until it either goes too expensive or not before we can migrate.
It's definitely the problem of having a long history. I spent too much time on my talk, and I'm really ashamed. But Nicola told me we should just don't skip the old thing and just talk about what we are doing now, because we have also this history, and backward compatibility is really a problem. Fabien, you wanted to make a comment?
Yes, just a remark. Thank you for all this presentation. Just Didier has left the Visio conference, so I can answer any question you want for Geomodelling too. Okay, so that's only this remark.
Okay, Miguel, you wanted to?
Yeah, no, I just wanted to add to the comment if open source is sustainable, because I agree. So if the expectation is that the project done by a PhD, which I was back in the day one, that's going to be sustainable, that's not a good idea. That is why it needs institutions that they are permanent to take those projects under their umbrella. So Geological Service is the obvious one, big companies, users in general. And it's super hard to go this transition from cool open source scientific project that someone has done in some institution to something worth maintaining that everybody's using. You have to be around for very long, which in our case in GenPy, that's our biggest merit. We have been able to survive for long enough.
Yeah, that's quite a success story indeed.
But still, I mean, at this stage today, it's still depending a lot on Florian's Institute and my company. And my company is not big enough to guarantee that we are going to be around 20 years. So that's why before anybody start really modeling the whole country with GenPy, it has to be clear that has